Let me just get this aligned properly. Okay. Anyways, oh, the screen's not down. Okay. So again, I apologize for starting a little bit late today. Part of the reason for that was a couple of people who came and asked me questions at the beginning, and I'm happy to answer questions all the time, but I didn't actually have time to plug everything in while that was going on. So, today is Thursday, June 5th. And here's sort of the list of what we're going to be going over today. So I didn't get any Money's Point cards last time with anything written on them, so I don't have any Money's Points to go over, which in some ways is a good thing because it means I've got more time to go through the new material, which is probably going to be, well, I don't know, I feel like it's about the same difficulty as the stuff we did on Tuesday's class. But it's still, fairly complex stuff to think about sometimes, so I want to make sure I've got lots of time to go over it. Again, as I mentioned before, there are some topics from Chapter 8 I'm covering, and other ones I am just completely not covering at all. So the way I've sort of set this up, 8.3.1 is sort of one of the topics from Section 8.3, which I'm covering fairly thoroughly. 8.8.1, the A sort of means additional. I wasn't sure how to quite label it. 8.8.1 is sort of my treatment about a bunch of things which in the textbook are sort of scattered throughout different sections, but are really all sort of different versions of the same thing. So you'll notice for 8.8.1, there are no practice problems from the textbook. The practice problems that are there are all ones that I've created. And the reason is because there aren't a lot of good practice problems on this particular subject in the textbook. So we'll see when I get to it, sort of with the examples and stuff. The way I create these sorts of problems is oftentimes different from the way the textbook creates problems. I think this is, I think it's an important, anyways, when we get to it, I'll sort of talk about it, and I'll talk about why it's sort of an important skill to be able to have, and why I'm disappointed the textbook doesn't cover it, but doesn't cover it at least in the way I do. And then 8.8.2 is another thing which is sort of, actually 8.8.2 is definitely, there are a couple things that are definitely in the textbook. I'm just adding some additional things in there to give you more examples. So again, if you look at 8.8.2, there's some problems with the textbook, and there's one extra one I've created because there was only one example of one particular type of problem in the textbook, and I wanted to give you another example of it. Yeah, and then once I've gotten through all that stuff, there's some group problems to go over.
When are we going to do homework on this section if there's a test next week?
Like, what do you mean, when are you going to do?
Are we doing our web assigned homework on this section and studying for the test at the same time?
Well, what I'm going to do is that hopefully the web assigned homework for this section is what you're going to use to study for the test. Okay. I would highly recommend that doing the web assigned homework will help to study for this test. Again, annoyingly, I will make sure that it's not due until the Friday after the test. And again, part of this is because there's no Thursday class next week. If there was a Thursday class next week, that's when the test would be. And the Tuesday's class, like part of that would be review. Part of it would be starting Chapter 7. Because there isn't a Thursday class next week, that's why the test is on Tuesday. But I'm going to make sure that the web assigned homework and the web assigned quizzes are not due till Friday next week. So if you don't want to use that as a way of studying, if you want to study using other methods, that you can do that later. That's the idea. So yeah, so nothing's going to be due on web assigned until Friday of next week. Just make sure that you can prioritize the test studying if you need to. Thank you for asking. Yeah.
Do you know where the answers are to the practice test?
I have not typed up the answers to the practice test yet. So once they're typed up, they will be on the course web page.
And 8.8.
8.8. Those problems that are on there, I have not had a chance to type up the answers to those yet either.
Oh.
So the ones that are in the textbook, they're in the textbook. The ones that I created, I have not yet had a chance to type up answers to them. So. I will do, hopefully, well, I'm definitely going to do the practiced ones after class today while I'm in the math center. When I'm not answering students' questions, I'll be typing things up. If I don't get to it today, I'll get to it tomorrow. But yeah, I will definitely try to type up solutions to all those things. There's other things like, other work that's needed to come first some of the time, but yeah. Any other questions before I get into the material for today's class? Again, just to mention again, there will be half an hour of review before the test on Tuesday. The test will not start until noon. So if you have extra questions you want to ask, well, again, come by the Math Center after class today, where I'll be there this afternoon. Come by my office hours on Tuesday if you have questions to ask me. That's usually an easier time for me to answer questions in full detail than before or after classes. Before class, I'm oftentimes trying to set things up. After class, sometimes I need to go and eat lunch. So yeah, Math Center during my office hours is the best time to come ask me questions. And the other thing I was going to say about the test, yeah, again, there'll be that half hour before for review. So if you have things you specifically know you're going to want to review already, put them on Muddy's point cards at the end of class today. And I also will, once I've gone through the stuff on Muddy's point cards, I'll take, show of hands for other topics to go over then. Yeah, and again, take a look at the practice test to see what sort of questions will be on the test. Okay. Anything else before we move on? Okay. Oh, this is last class of Muddy's point. Oh, there we are. Okay. So, Chapter 8 is called Further Applications of Integration. It's basically a collection of a whole bunch of different applications of integration. There are a bunch in there I'm just not covering. There's some stuff on volume and surface area the arc length and surface area that I'm not covering because most people don't really ever go on to use that. It's one of these things that, it's interesting from a mathematical point of view. People who are going to, spend a lot of time doing geometry, it's definitely interesting for them. But I'm guessing most people in the class are not going to be doing a lot of geometry, so that's why I'm focusing more on the stuff that comes from other disciplines. So the first section, hydrostatic force and pressure, this is a section on basically engineering type problems. How do you figure out, how thick you need to make a dam, sort of type situations, how we can apply integrals to those types of things. 8.8.1 is about, again, this is sort of additional topics that I've sort of collected. It's a bunch of ideas that are in different places in the textbook, and again, they're not really, I don't think they're very well organized, but it sort of just talks about the idea of what it means for something to be a sort of density, like a population density, or a mass density, or a energy density, or those sorts of things, and how we can sort of apply integrals to any sort of problem which involves those sorts of ideas. And 8.8.2 is a collection of a couple other problem types that might come up that I just wanted to go over. So I'm going to get started on section 8.3.1, which deals with hydrostatic force and pressure. And what this sort of idea is useful for is figuring out how much force has to be exerted on a rectangular dam, which is 100 meters wide, 20 meters tall, if the water level is 2 meters below the top of the dam. So again, these sorts of questions come up fairly frequently in engineering type situations when you're trying to, measure how thick you need to make a dam, how thick you need to make the walls of an aquarium, those sorts of things. As you measure force and pressure. How many people feel like they've solved problems like this before? Maybe even if you've done it in your physics class. How many people, feel like at some point they were taught this and they totally forgot it? And I guess, how many people have never seen something like this before at all? Right. So again, it's probably going to be new to you, most of you. I will try to cover it in such a manner that understanding the physics concepts is not necessary to actually be able to solve the problems. Again, all the physics equations will be on the formula sheet on your test. Yeah. So, the key thing to mention is that when you're building a dam, you're building anything that's designed to hold back water. What happens is the water always exerts pressure on it. The water exerts a force on it due to the water pressure. This type of force is called hydrostatic force. The hydrostatic force in water depends upon two things. It depends upon the pressure, or how much pressure does the water have. It also depends upon the area over which the pressure is exerted. So the force is the pressure times the area. One thing to mention is that water pressure itself depends upon two different things. It depends upon the density of the liquid and the depth below the surface. I'm using row here rather than, anyways, I use mu somewhere else in row here. I'm not entirely sure why it switched. But anyways, the pressure is the density times G times the depth. I think on a, oh, anyways, sorry, is there extra copies of the formula sheet back there? Somewhere? Yeah, sorry, I just wanted to check how I did on the formula sheet. So. Okay, yeah, I did use different symbols in the formula sheet. Anyways, these two guys, for this purposes of this class, those are the same thing. Those are both density. Both those symbols are two different symbols for density. I don't know why they're used different symbols. Anyway, why the book uses different symbols in different sections, but they're both density. But the idea is if you want to measure water pressure gets higher the deeper you go in the water. So water pressure is the density times G, which is basically the thing that measures gravity, times the depth. So what this means, if you put those two formulas together, the force is the density times G times the depth times the area. So this is the formula we're going to need to use when we're trying to calculate the force that's exerted on the dam. Force is the density times G times the depth times the area. And again, that stuff is all going to be on the formula sheet. Any questions about this at this point? Okay. So one thing to mention is the pressure is different at different depths, right? I mentioned at the bottom of a pool full of water, or anything full of water, the pressure is higher than it is at the surface. What this means is if we're going to calculate this thing, we can't just take this number times this number times this number times this number, because these things are not going to be numbers, they're going to be formulas. Right? So if we're trying to calculate what the force is going to be, we're going to use an integral. Because as we go deeper, the force or the pressure is going to change. The depth is basically changing as you go deeper. So we need to set up an integral to evaluate. So the idea is that when you're trying to set up an integral to evaluate something, the first thing we need to think about is how can we approximate it with a Riemann sum. So when we're doing that, let me just draw a picture. Let's suppose you have a dam like this. There you've got a dam, and you've got some water level here, some water that's resting against the dam. So the idea is when you try to measure the force on this dam, the pressure is going to be different at different heights. So what I'm going to do is I'm going to slice it this way. I'm going to take different slices of the dam. They're going to be horizontal strips. The reason they're going to be horizontal strips is because different places at the same horizontal level will have the same pressure. If we used vertical strips, the pressure would be different on different parts of the strip. So we want to take horizontal strips because then the pressure is the same everywhere on that strip. Usually, in these sorts of situations, I will measure y down from the surface of the water. So the idea is, here the depth is just y. And again, oftentimes you'll call it yi star, and that'll sort of represent the sample depth. It'll either be like the top of this interval, the bottom of this interval, the middle of the slice. Delta y is the height of that slice, or the width of that slice, right? Now if we want to find the area of the slice, what we've got to do is we've got to measure the width. And again, the width is going to depend upon where we're taking our sample point, so it's going to depend upon yi star. So the area is always the width times the height of the slice. And if we want to find the pressure, we've got to take the depth times the area times rho times g. So the Riemann sum formula for the pressure is going to be rho g yi star w of yi star delta y. Right, we're adding together each slice, and each slice, the force on each slice is the density times the g times whatever the depth is times the width times the height of the slice. And if we turn this into an integral, we get this. The integral of rho times g times the y, which is, again, the depth down from the top, times the width as a function of y, dy. Now, if we're integrating, we're always integrating from, y equals 0 at the surface of the water to whatever, I don't know, y d, the bottom of the water. We're always integrating from the surface of the water down. Now, one thing to mention here, usually in these sorts of problems, I will measure my y-axis down from the surface rather than up from the bottom because it makes the formulas a little bit easier to work with. Some people will, if you measure your y up from the bottom, you should still be able to get the same answer with some slightly different formulas. These things usually work out better if you measure your y-axis down from the surface. Are there any questions at this point about where this integral formula came from? Again, this skill of being able to take a physics formula, like the one on the previous slide, the force equals rho g dA, being able to take a physics formula and turn it into an integral formula is an important skill, right? That's sort of what I'm trying to teach at this point of the course, right? It's how do you take a physics formula like this and turn it into an integral formula like that? And the answer is what you do is you take the thing in question, you cut it up into pieces, you slice it in one direction or another, measure what this physics formula gives you on each piece, turn that into a Riemann sum, turn the Riemann sum into an integral. Any other questions about this before I move on? Okay, so I'm going to do some examples of these sorts of problems involving measuring hydrostatic force and pressure. So here's example 1. Here we have a triangular plate, which is a base 4 meters, height 5 meters. It's submerged in water with a point at the surface of the water. So here's the surface of the water. We have a triangle like this. And it's submerged in water. And you want to find the hydrostatic force against one side of the plate. So again, this might not be a dam in this situation. This might be someone's underwater, I don't know, it's the side of their underwater habitat. They're building an underwater city, and this is what the side of it looks like. It's kind of an underwater tent or something like that. Anyway, I'm trying to think of something that would look like that, a situation where we have pressure exerted on that. They want to know how strong do we need to make this side of the tent, right? What sort of force does it need to withstand? Well, the idea is we're going to slice this thing like that. We're going to take strips of this thing at the same depth, because things at the same depth will have the same pressure. And again, we always measure our y-axis down from the top, from the surface of the water. And so the key thing is to use this formula, we need to have a formula. So the density, by the way, for water, the density is 1,000 kilograms per meter cubed. That's the density of water. So that guy's already there. G is 9.8. Right? Those two things are basically fixed. They just depend upon, like this just depends upon what sort of liquid we're dealing with. The y is just y, but it's this width part that we need to figure out what it's going to be, right? We need to figure out what's the width of this slice going to be and how does that depend upon the depth. Well, the idea is we have two triangles here which are similar. One triangle has height y and width w. The other triangle has height 5 and width 4. And those two triangles are the same shape. They're what are called similar triangles. So the ratio in the big triangle should be the same as the ratio in the little triangle. This is because of similar triangles. So we can rearrange this to get a formula for the width. 5w equals 4y, so w is 4y over 5. So we will get the integral. Now, the y is going to start at 0 at the top of this thing. The biggest y is going to get is going to be 5. So the integral is going to go from 0 to 5. We're going to have 1,000 times 9.8 times y times 4y over 5 dy. Right, that's what our integral is going to look like. So now all we have to do is integrate that. So 1,000 times 9.8 is 9,800. That can come out front. Here we have 4/5 y squared dy. So if we integrate 4/5 y squared, we'll get 4/5 y cubed over 3. This whole thing's got to go from 0 to 5. So we have 9,800 times 4/5 times 5 cubed over 3 minus 0 cubed over 3. And again, as mentioned, you can just leave it like that. You don't need to actually simplify. Use your calculator to figure out what that actually equals to. By the way, one thing I'm going to mention now, I mentioned this to a couple of people, person to person, a little bit earlier. The idea is, in half of the applied questions on the test next week, I'm going to ask you to set up but not to evaluate the integral, which means in that situation you stop here. As soon as you have an integral sign and something inside of it, you stop. You don't need to do this step of going through and actually finding the antiderivative and integrating it. So if I say set up but do not evaluate an integral, this is where you would stop. And again, the reason for this is because if I ask you to evaluate every single integral that's on the test, some of them will take a really long time to do because they'll be complicated. Some of them are just sort of not worth doing because they're complicated. And it really means that I can't ask as many questions on the test because each question will take you a lot longer to do. So in general, if I say set up but do not evaluate the integral, you stop here. If I say actually evaluate the integral, you can stop here. If you want, you can find out what this is using your calculator, but you don't have to.
Sorry, with this picture, I'm just having a little bit of trouble because I'm picturing the x-axis as being at the level of the water, so shouldn't the depth be negative?
So
like, do you have it flipped upside down?
I have the y-axis measuring down from the top.
Yeah.
This is why I put the so if you want, you can actually say y goes from -5 to 0.
Yeah. Okay.
And you can make this a 4 times negative y over 5 to sort of mention that the distance is actually not y, it's negative y. If you want to do it that way, you can. I usually just think about y as something which is 0 here, 1 here, 2 here, 3 here, 4 here, 5 here. Right?
It's basically like it's flipped on its point.
Exactly.
Okay.
Yeah. Yeah. So again, this y-axis is not the normal y-axis. Normally, things below are negative on the y-axis. This y-axis, things below are positive. And again, that's just the way that you measure depth in general. And below the surface are positive.
On the exam, do we have to specify where the origin is?
Well, if your final result looks good, no. If you have weird stuff that happened in your final result because you put the origin in a weird place, like I guess what I'm saying is that if you get an integral which doesn't make sense, you can get part marks for having a well-drawn picture. Right? If you don't have a nice well-drawn picture like that with the actual which distance is y labeled, you won't get as many part marks. So that's the key thing. Is it really, this is not a necessary, like, definitely I want you to, write out this sort of information. Right? Write out all the calculations you're using to come up with this formula. Right? This much showing your work I definitely want to see. The picture is nice. It's not necessary if you're one of the people who really is, doesn't like drawing pictures. But again, if the final answer is incorrect, I'll be looking for a picture to give you part marks. So, yeah. Okay, so example 2, here we have a milk truck which is carrying milk with a density of 64.6 pounds per foot cubed. And it's in a horizontal cylindrical tank with diameter 6 feet. So you got right, this is a milk truck. Anyways, so it's a cylinder. The diameter of the cylinder is 6 feet. Right? So we want to set up but do not evaluate an integral for the force exerted by the milk on one end of the tank. So we want to figure out what the force is going to be exerted by the milk on that thing. Sorry, this is example 2. So I'm going to draw a picture of this circle. And what I want to do is I want to measure the width. Right? Find a formula for the width in terms of, now again, this thing is going to be full. Sorry. So here, the y is the distance down from the top. Now, what I'm going to do in setting up the integral here is, so here, let's say this is the center of the circle there. The radius of the circle is 3. Right, so the distance from the center to the outside is 3. This distance here, so this distance is y, so this distance is 3 minus y. Right, that distance there, so this is y, this is 3, so that's 3 minus y. So here we have, and this distance here is w over 2. So we have, using the Pythagorean theorem, w over 2 squared is 3 squared minus 3 minus y squared. So w over 2 is the square root of 3 squared minus this guy. W is 2 times this square root of 9 minus 3 minus y squared. So that's the width. Right, this is another formula for the width. The density is 64.6. The G is 1, because when we're using imperial, the units work out if you measure the units correct. Like in pounds force per pound of weight, G is 1. So if you want to set up an integral, well, we're going to figure out where y starts at the top, that's y equals 0. It ends at the bottom, which is y equals 6. So the y-axis will go from 0 to 6. We'll have 64.6 times 1 times y times the width, which is 2 times square root 9 minus 3 minus y squared dy. You notice I didn't ask you to evaluate this integral, and one of the reasons is because this is a really ugly integral. It's got a square root with another function inside of it. Those sorts of integrals are generally difficult integrals to evaluate, and I'm not going to make you do that once you've sort of done this hard thinking of actually coming up with it in the first place. So any questions about where that integral came from? Yes?
Why is G1 again?
Why is G1? Because we're working in imperial. So, and again, if I give you, now one thing to mention is on the test, everything will be in like kilograms and meters. Everything will be in metric on the test. There are some WebAssign questions that have imperial units like foots and pounds, stuff like feet and pounds, stuff like that. In that case, always use 1 for G and everything will work out. Again, I don't really want, trying to explain why that works out has to do with the fact that like the people who are writing this textbook aren't doing physics in imperial the way that physicists who use imperial actually do physics in imperial. So that's why I sort of gloss over it a little bit, because it's, yeah, it's difficult to explain, and I don't really, again, there's not, on the test it's all going to be in meters and kilograms and stuff.
So on the test, do that by
do 9.8 on the test. And that actually, if you notice on the practice test, there's one question which uses G, and I said hint G equals 9.8 on the test. So now, part B, I want to repeat this whole procedure, but here the tank is going to be half full rather than completely full. So if the tank is half full, the water level is going to be here, right in the middle of the tank. And if we go a distance y down from the water level, so this, a slice is going to look like this green thing down here. Here, half of the width is actually on a triangle with 3 and y, rather than with 3 minus y, because here I'm measuring y down from where the water level is. So, in part B, rather than being a 3 minus y squared, it's just a y squared. Right, because that just is y rather than 3 minus y. So W over 2, rather than 3 squared minus 3 minus y squared, is 3 squared minus y squared. Here, W, rather than being 2 times the square root of 9 minus 3 minus y squared, which is 2 times the square root of 9 minus y squared. These guys are still the same. So this whole thing will become a lot simpler. It's just now square root of 9 minus y squared. But limits of integration are also going to change. Here, we start at depth 0. The bottom of the tank is now depth 3. So here the integral goes from 0 to 3. So again, for part B, a lot of it looks the same, but there are a few things that change. And those change mostly based upon the fact we're measuring the depth now from a different place. The surface of the water is now at the middle of the tank rather than the top of the tank. So what's now here is part B. Any other questions about this example? Yes?
Where is 0 if the tank is half full?
0 is here. Right? If I'm measuring y like this, that means depth 0 is here, depth 1 is here, depth 2 is here, depth 3 is here. So 0 should always be at the surface of the water. Now, if you do it a different way, it's not wrong. But if you do it a different way, just make sure you've labeled a picture with that thing on it, so I can tell if we've done it differently. Any other questions about this? Okay. So I'm going to move on to the next section, which is 8.8.1. And 8.8.1 deals with different types of density. So for example, this problem here is one that deals with population density. Here we have a rectangular city which is built along the coast, and the population is most dense at the coast and less dense inland. And the density turns out to be 1,000 times 2 minus x per people per square kilometer. And we want to find the population of the city using that population density. And so the idea is what I'm going to be talking about here is basically how do ideas of density relate to ideas of integration? How can we turn a problem about density into an integral in order to evaluate it? How many people feel like they've either seen questions like this before or feel like they know how to do it because they have a good understanding of what's going on? Anyone? A bunch? How many people feel like have never seen something like this before? How many people, is there anyone here who's seen something like this before but don't remember how to do it? Okay, let's see your hand saying that, yeah. Anyways, again, it's one of these sort of things that if you can understand what's going on, these problems should not be difficult. And the key thing I'm just going to talk about is that there is this idea of density, and there are different types of density, and you deal with all those different types of density using the same mathematics. The actual math behind the different types of density is the same in every single situation. So there's three different mathematical types of density. Three different mathematical types are linear density, area density, and volume density. So for example, linear density measures the amount of something per meter. So some of the examples from the last section, from section 6.4, had situations where we're measuring something's weight per meter. How many kilograms per meter is this rope? Right, that's an example of linear density. It's something measured per meter. It's something that's long, and each meter of it has a certain weight. Or here it could be dollars per meter. What's the cost of rope per meter, right? That's when people sell rope, they measure the price in dollars per meter or dollars per foot. So if you want to find the amount of quantity in a long object, you take the linear density and you multiply it by the length, right? If you have a linear density, you multiply by the length to get the thing in question. If you have an area density, you're measuring the amount of quantity per unit of area. For example, if you have sheet metal, then its weight might be in kilograms per centimeter square, right? Now, if you want to find the amount of the quantity in a piece of the object, you take the area density, you multiply it by the area. So if you have like a piece of sheet metal that's like 10 square meters, and it weighs 0.01 kilograms per square meter, you multiply the 0.01 by the 10 to get the weight. And then there's volume density. And volume density is amount per unit of volume. So something like joules per centimeters cubed is a volume density. If you want to find the amount of quantity in a piece of the object, you take the volume density, you multiply it by the volume. So the key thing is in dealing with any sort of density problems, the first thing you need to do is you need to be able to identify which type of density is it. Is it a linear density? Is it an area density? Or is it a volume density? It's a linear density if it's measured per meter. Right? It's an area density if it's measured per something squared. It's a volume density if it's measured per something cubed. Right? That's the idea, is that what am I trying to say? What type of density it is, mathematically speaking, depends upon what the units are. That's the easiest way to figure out, whether it's linear, area, or volume density, is by looking at the units. So, and the idea is if we know the density of any quantity, we can always find what the quantity is using an integral. So if we know the linear density, we can find if we know the price linear density, how much it costs per meter, we can find the actual cost using an integral. That's the idea here. Any questions about the idea of linear, area, volume density before I move on? Okay. So, again, those are sort of the three mathematical types of density, right? Whether it's a linear density, area density, or volume density. In the real world, there's a whole bunch of different kinds of density, right? You can talk about the density of mass. You can talk about the density of population. You can talk about the density of cost, right? That idea of dollar, the price of a rope is density of cost. And each of these different types of density can be applied in different situations. So the most familiar type of density is mass density, which measures the amount of mass per unit of length, area, or volume. Now, if you want to calculate mass, what you've got to do is you've got to take the mass density and multiply it by the length, if it's linear, multiply it by the area, if it's an area density, or multiply it by the volume, if it's a volume density, and turn that result into an integral. Again, this process of turning it into an integral requires sort of being able to write out that Riemann sum and turn it into an integral. So here we have a liquid which is in a cylindrical tank of radius 3 meters and height 5 meters. And it's more dense at the bottom of the tank than it is at the top of the tank. So you have a tank that looks like that. Right? The radius is 3, the height is 5. And it's more dense at the bottom than it is at the top. So the density is given by that formula. 100 times 10 plus d kilograms per meter cubed at a depth of d below the surface. Well, d here is measured from the surface, right? So now we want to find the mass of this liquid. So in order to find the mass of this thing, the key thing is we can't just take the density times the volume. And the reason we can't is because the density here depends upon the depth. The density is not just a number, it's a function. So whenever we have something that's changing, we have to integrate it in order to figure out what the mass is going to be. The first thing I'm going to mention is that the mass is the density times the volume. And again, the reason is because it's a volume density. It's measured per meters cubed. So if you want to find the mass, you want to take the density and multiply it by the volume. Now we're going to have to cut this thing up into slices. because this density changes. Now, density changes with how deep it is below the surface. So we're going to want to integrate this way. We're going to integrate with respect to the depth, which means we're going to want to take slices that look like that green thing there, right? We want to take horizontal slices because we want to take slices that are at the same depth. If those slices are all happening at the same depth, they will all have the same density everywhere in that slice. So the key thing is we need to know, well, what's the density? Well, the density here is just 100 times 10 plus d. Right, that's the formula for the density. Now the volume, how are we going to calculate the volume of this slice? Well, this is a cylinder. The volume of a cylinder is pi r squared h. Pi times the radius squared times the thickness of the slice. Again, it's because the area of this circle is pi times the radius squared. Now the radius here is just 3. The h here is going to be delta d. Right, the thickness of this slice is always basically, depending upon how many slices we take, that's going to determine the thickness of the slice. It's going to be delta, whatever the variable is we're integrating with respect to, which in this case is d. So if we want to find the mass, we're going to take the density and we're going to multiply it by the volume. Right, this gives you the formula for the mass of a slice. You can take the formula for the mass of a slice, and we can turn it into a Riemann sum. Right? Just bring a sum symbol in front. We can turn that Riemann sum into an integral. I'll write it as 900 pi 10 plus d dd. Now, I realize using d as a variable was a little bit confusing here because now we have a dd rather than dx or dy. If I call it x, it would be 10 plus x dx. It would give you the same thing. And the key thing is we need to figure out what is the range of d. Well, d starts at the top of the tank, that's d equals 0, and ends at the bottom, which is d equals 5. So we will get an integral that looks like this. Now, I realize I didn't write this into the question, but I had intended to just set up but to not evaluate this integral. Again, I could evaluate this if I wanted to. Time-wise, I want to talk more about how to set up future integrals rather than how to evaluate this one. So I'm going to move on to other examples, but this is how you set up this integral. Yes?
On the exam, on the midterm next week, does it matter if you write out the Riemann sum? I assume it's like
If you get,
skip a step.
yeah, exactly. No, so you're right. You can sort of skip the step if you want, because this step is just you put a sum symbol in front, you turn that into an integral.
So we won't lose marks.
You won't lose marks if you don't write it out. Yeah, exactly. And that's something actually I should mention. Maybe I might actually do that for some of the future examples as well. I'll sort of skip this Riemann sum step. I'll just say, here's the formula for the mass of one piece. Putting an integral sign in front will give you the formula for the mass of the whole thing, provided that I turn the delta d into a dd. That's the idea. Any questions about example 3 here? Okay. The next example is going to deal with population density, which is another sort of familiar type of density. Population density measures the number of individuals, either people or animals or whatever, per unit of length, area, or volume. We can find population by you take the length, area, or volume, we slice it into pieces, multiply the length, area, or volume of each piece by the population density, and adding up the results. Again, if it's a linear density, you multiply the density by the length. If it's an area density, you multiply the density by the area. If it's a volume density, you multiply it by the volume. So here we have a circular city. Its radius is 10 kilometers. The population density of the city is 3,000 over r plus 1 people per square kilometer. And so then what we want to do is we want to set up, but do not evaluate, an integral for the population of the city. So let me just draw what's going on. So we have a circular city, and it has a radius of 10 kilometers. And the idea is, in the center, we've got a lot of people living downtown. As you move out from the center of the city, there's less and less people living farther and farther out. So if we go out to a radius of r, the density is 3,000 over r plus 1. Now, one thing to mention is, one of the annoying things about this problem is that you can't slice it with horizontal strips or with vertical strips. And the reason is because you do horizontal strips. Let's say you've got this horizontal strip here. The density is still going to be highest at the middle of this horizontal strip and lowest at the edge. We can't take horizontal strips and have it be the same density all the way across. We also can't take vertical strips and have it be the same density all the way across. What we have to do in this sort of situation is we have to integrate with respect to r, which means we're going to take circular strips. We're going to actually slice it into pieces that look like that. So take a middle piece, one piece out, one piece out, one piece out, one piece out, one piece out. So he slices this way. So we're taking a slice at each radius. The radius starts in the middle and goes to the edge. Now here this is an area density because it's people per square kilometer, right? So here, the population is the density times the area. Now, the other thing to mention, how can we find the area of a blue strip like that? Well, if we want to find the area of it, it turns out that the area of a circular strip like that is just the distance around, which is called c, times the width of that strip, which is delta r. It's basically, if you straightened it out, it would basically be a rectangle. It's close enough to a rectangle you can approximate its area using sort of length times width. Now the length here is a circumference, is the distance around this strip. The circumference of a circle, as you probably know, is 2 pi r. Now, there are enough examples with these circular strips in them that if you want to just memorize that the area of a circular strip is 2 pi r delta r, that's totally fine. You don't necessarily need to understand where this area formula comes from, but that is where it comes from. If you've got a circular strip, you want to measure its area, you're going to take the width of the strip times the length of the strip. Basically, if you sort of straighten it out, it would be a rectangular strip. If you want to measure the length is really the distance around it. And so that's where we get. So, the density here is 3,000 over r plus 1. The area is 2 pi r delta r. And we can take this and we can turn it into an integral. And we turn it into an integral. The delta r becomes dr. The other thing we need to figure out, of course, is the limits of integration. Well, the lower limit is the smallest r can be. Well, the center of the circle, r is 0. At the edge of the circle, r is 10. And so this gives you an integral, which represents that population. So I just want to mention, again, that in this example, the slices, rather than slicing it horizontally or vertically, we actually slice into these circular bands. And the reason we're doing circular bands is because those circular bands will have the same population density everywhere around that band. Any other questions about this example? If you know how to do double integrals, you are allowed. Yes, you are allowed to do double integral. If you know how to do double integrals. Yes. If you know how to do it, you're allowed to do it. I was going to say, yeah. If you've taken or if for whatever reason you've learned double integrals before, yes, this can be done with a double integral. I think it's easier to do without one, but yes, if you want to do it with a double integral, I'm totally fine with that, as long as it's set up correctly and it actually works. You know, yeah. But yeah. Oh, by the way, if you're doing it as a double integral, I want you to not just leave it as r, but actually express it in terms of x and y, like that sort of stuff. Yeah. Okay. So another type of density is what's called energy density. So energy density could be measured in like joules per cubic centimeter. Lots of types of energy are distributed types of energy. They're not all like stored in one place. They're sort of spread out. So heat energy is an example of energy which is spread out. It's distributed. It has an energy density. Heat energy can be stored in varying amounts in different parts of an object. Light energy can have the same sort of density, right? If you have a solar panel, you've got a certain amount of light falling on each part of the solar panel, and you sort of want to measure, maybe there's more light falling in the middle of it than there is at the edge because of the shape of the solar panel, and you want to figure out the total amount of energy that solar panel's getting, then you need to have this idea of energy density in there. Now, energy can be measured in joules. There's a closely related thing to energy called power, which is measured in watts. This course, you don't need to be able to differentiate between energy and power. But if you see joules per unit of length, joules per unit of area, joules per unit of volume, watts per unit of length, watts per unit of area, watts per unit of volume, those are all energy densities. And all those sorts of things can be evaluated with integrals using the same sort of approach as we've seen here. So here we have a 10 millimeter long light bulb filament, and it's made such most of the light energy is emitted from the middle of the filament. So it emits more light from the middle of the filament than it does from the edges. And at position x along the filament gives off 10x minus x squared watts per millimeter of light energy. And then we want to find the wattage of the bulb. How many watts is this bulb going to be? Well, here's your light bulb filament, just a thin wire. And the idea is that at position x along the wire, the filament gives off 10x minus x squared watts per millimeter. So, if we want to figure out the energy, and again, in this case is actually technically power and not energy, but I'm glossing over the difference for this course. The amount of energy is going to be the density times the length. Now again, here the density changes at different places in the wire, which is why you can't just take the length and the density, multiply them together, and get an answer. Right? We're going to have to set this up as an integral. So the key thing is, what we're going to do is we're going to cut this filament into pieces. And we're going to look at a certain piece and figure out how much energy or how much power is going to be emitted by that particular piece. Well, the length of that piece is delta x. Right? That's how long that piece is. Cut up into pieces like this. The density is just 10x minus x squared. Right? So that's the formula for the energy in one, or the power emitted by one piece of that filament. It's the energy density times the length. And if we turn this into an integral, we get that. The integral of 10x minus x squared dx. And the key things here is just to figure out, okay, what's the limits of integration? Well, this side is x equals 0. And this one is x equals 10. Because it's 10 millimeters long. By the way, I just realized that this question's a little bit ambiguous because I said at a position x. I didn't say where the position x is measured from. In this sort of one, if it was on the test, I'd give you a picture. I'd sort of draw this filament. I'd show how x is being measured, just to make it clear what that represents. So the integral is going to go from 0 to 10. So linear density problems are usually really easy. Usually if it's a linear density, all you have to do is multiply by delta x, which becomes dx. So that's the other thing to mention is, yeah, anything which is per meter, per millimeter, usually you just have to integrate whatever thing you've been given. Oh, and this one I can, yeah, I've got time to integrate this. If you integrate this, this gives you 5x squared minus x cubed over 3 from 0 to 10. Plug in 10, that gives you 500 minus 1,000 over 3. Plug in 0, that gives you 0 minus 0. 1,000 over 3 is about 333, so this is 166.6 repeating watts. And the wattage of this bulb is. or you can write it as 500 over 3. So it's a pretty bright light bulb. I mean, it's not like a 500 watt bulb, but. Oh, I don't know. I just realized I could have made this picture. Again, if this was something that was happening with the test, I probably would have drawn an actual light bulb with that thing inside of it. But anyways, this is the filament in the light bulb. It's the part that actually emits the light. It's a really thin piece of wire. Any questions about this example? Again, linear density problems tend to be easier than the other types because you don't have to worry about formulas for area and volume. Okay, so last example before the break is an example of price density. And this happens in situations where objects have a price per unit of length, area, or volume. So again, when you're buying rope, you buy it by the foot or by the meter. When you buy sheet metal, you usually buy it by the square foot or square meter, right? If you buy dirt, you buy it by the cubic foot or cubic meter. So the units here are going to be dollars per meter, dollars per square meter, dollars per cubic meter, that sort of thing. So here we have an excavation company who's been contracted to dig a trench in the shape of a triangular prism, 1 meter wide, 1 meter deep, 2 meters wide at the top, and 100 meters long. So they've got to dig a trench. Now the price this company charges to dig a trench is going to be $10 times 1 plus D per cubic meter of dirt. And D is the depth of the dirt below the surface of the ground. What this means is the deeper they're digging it, a trench which is really narrow and deep costs more than one which is wide and shallow, even if it's the same amount of dirt they're digging out. The reason is because it's harder to dig deeper holes. So they're going to charge more if it's going to be deeper. So deeper holes are more costly to dig. So now we want to find how much they're going to have to charge for this excavation. Okay, that's the formula they use to charge it. So the first thing to mention is that this thing, well, actually no. So the first thing I'm going to do is I'm going to show you a draw picture. So there's the triangular trench. So it's 1 meter deep. It's 2 meters wide at the top. And it's 100 meters long. So the next thing I'm going to mention is that the price is the density times the volume. Now, the reason I'm multiplying by volume here is because it's measured per cubic meter. It's measured per unit of volume. So what I'm going to need to do is I'm going to take slices of this and find the volume of each slice. Now when I take slices, I'm going to take slices like this green one here. I'm going to take slices at a constant depth. And the reason is because it's with the depth that the price changes. Right, so I take stuff at the same depth that's going to have the same price all the way around. So I'm going to measure my D down from the top of the pyramid. Now the volume, this slice, is basically almost a rectangular prism. The volume of it is going to be the length times the width times the height. Now the length of this thing is 100 meters. It doesn't matter how deep it is, the length is always the same. If this thing's always going to be 100 meters long, it's going to change the width. The width, I'm going to find a formula for later. The height is basically the thickness of this thing, which is delta D. Right, when you're taking slices, the thickness of that slice is always delta X or delta Y. Here the variable I'm using is D, so the thickness is delta D. Now what I need to do is I need to find a formula. So this is D, I need to find a formula for that width. Right, what's the relationship between width and D? Well, the idea is this blue triangle and this green triangle, they're similar triangles, right? The green triangle is 2 meters wide and 1 meter deep. The blue triangle, this distance here is 1 minus d, and that distance there is w. So 2 over 1 is w over 1 minus d. Right? The ratios are the same because they're a similar triangle. The width over the height is the width over the height. If you cross multiply, you get 2 times 1 minus d equals w. So now we have a formula for the width. So the volume here is going to be 100 times 2 times 1 minus d delta d. Any questions about how I work this stuff out? The formula for volume and such. You know, that diagram is not as nice as it could have been. That arrow is sort of superfluous. So this distance is the width, this distance is 1 minus d, this distance is d, and this distance is 1. And with the big triangle, the green triangle is similar to the blue triangle. So the ratio in the green triangle is the same as the ratio in the blue triangle. So the price here, the density is 10 times 1 plus d. The volume is 200, 1 minus d, delta d. So if you want to measure the total price, you just got to turn this thing into an integral. Now the integral is going to go from the top of the trenches d is 0, the bottom of the trenches d is 1. Right, at the top the depth is 0, the bottom the depth is 1. Times 10 times 200 is 2,000. 1 plus d, 1 minus d, dd. And again, this is another example where I wouldn't ask you to evaluate this integral, just set it up. Any questions about this before I give you your break? Yes?
How do you get dd?
Delta d becomes dd. Delta x becomes dx, so delta d becomes dd. Yeah, whenever you turn it into an integral, that thickness becomes the dx, the dy, the dd, whatever it is. Yeah. Again, hopefully if I do something like this, I'll use a letter other than d. Someone when I was coming up with these slides, I didn't actually think about the fact that d is ambiguous. But, yeah. Okay. So, sorry, I thought I heard someone talking. Anyways, so just before the break starts, I'm going to hand back the quizzes that are marked. Yeah, generally, this one was harder than the first quiz. So generally, of course, the class average is lower. I mean, it's not bad by any means. It's still pretty good, but yeah. I think that's. Anyways, if anyone has any specific questions about quiz questions or how I mark them or whatever, please put up your hand and ask me. And yeah, I will scan after class. I'm going to scan these answer keys. I'm going to put them up on the course website. So Abby first, and Brian, and Dave, Michelle, okay, Mike, and Kate, and Kyle. I thought it was usually just use big eye contact. Dylan. Maya. And Shelly Moore. Yeah. Interpreet. And Ellen. And Danielle. And Joel. Oh, there you are. I was watching Marlo. And Alicia.
Yeah. I can't.
And Harleen.
I'm really bad at that.
And Harleen.
Especially in, you know, with Ben, if you didn't
Daryl. Yes. And then here.
No, I'm pretty sure you can get extra showing.
Yeah.
Yeah.
Chen. And Dimitri. And Holland. And Deborah. And Lovey. And Ryan. Jackson. And Brandon. One? Yeah.
I have you.
Yes.
Oh, where? You're right, you did put it there. Okay, I'm gonna change that. Thank you. I don't know how I didn't see that. There were some people who I thought, I don't know, for some reason, there was someone else who, some people wrote exactly the same as you, but then the brackets they had put in meters per second. And that's, anyways, and somehow I thought your answer was the same as theirs for some reason, but yeah, you should have gotten four there. Thank you for pointing that out. I don't, yeah. Clearly I was thinking of someone else's when I was going to yours or something. Yeah.
And take everything here.
Yeah, exactly. No, but I mean, it's totally my mistake, so. Yes.
I just have a question here. Why is that incorrect? Like, I'm just saying it represents the net change in the first 3 minutes that the water's flowing.
Okay, gotcha. I thought you were trying to put the of flow up here, the net change of flow of water. or something
No,
like
I was
that.
saying
Okay.
just like the
First
net,
3 minutes
the
of
net
flow.
of the water. That's
Okay, that makes sense. Yeah, because again, I think I did the same thing with yours as I did with something else. There was someone else who had something very similar and was
Okay.
like.
I see,
Yeah,
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 because
yeah.
if you put it up here, then
Yeah,
you're
no,
meaning that
exactly.
it's, yeah, I'm
Just
not
somehow
talking
the
about the
flow
years, I'm
is
just
changing.
talking, yeah.
Okay, no.
I'm just talking about
That's then
the while
first
the
3
water,
minutes of
it flowing.
That makes sense too. Yeah.
There we go. Okay, yeah, thanks.
Actually,
You'd think in math there wouldn't be as much ambiguity.
All the problems come from language.
Yeah, it's only because I like asking questions that require answers in words. That's just my, yeah. Oh, let me turn off the projector. I just realized I was about to show everyone's grades on the screen because I was changing your twos, but.
Is my quiz up here, or did I
Oh,
miss it?
yes. Where are you sitting when I
I was sitting right there.
Okay, for some reason I thought you sat farther back, and I was looking for you farther back. and I
Okay,
didn't see you.
okay.
It's Ryan, right?
Yes, that's
yeah.
right.
Okay.
Thanks.
Yeah, I don't know why I never remember calling out your name and not seeing you.
Oh, that's all right.
Yeah.
We got like plenty of extras.
Oh yeah. Are there actually that many? I guess there's that many people who's not here today.
I got a question. I keep forgetting the area. I mean the width. Like I keep forgetting.
So the idea is I'm trying to figure out this distance.
Yeah.
And I notice when I draw this picture, this blue triangle and the green triangle are similar triangles.
Okay.
Right? This distance is D.
Yeah.
That's the depth. That's where you measure that.
Okay.
This is D. This is 1. This is 1 minus D. Right? So when the blue triangle and the green triangle are similar, so the ratio of the blue triangle and the ratio of the green triangle are the same.
Oh, okay.
And then just rearrange them. Yeah. Yeah. The similar triangles things, I mean, it depends how people did calculus 1, but a lot of the like related rates problems and stuff are the same idea. Yeah. Yes. So did you get the practice test? Did you get? You probably didn't get any of them. So let me just grab one of each. Here's 2, and there was one more that should have. It's got to be stuck. Sorry.
Thank you.
You're welcome.